Okay. So thanks a lot, Hiroshi, for giving the talk on open closed homotopy algebra in superstring field theory. So you have 1 hour and a half, which you can organize as you want. Thanks. You can start when you're ready.
Okay. Before starting my talk, I would like to thank all of you for starting the journal club 1 hour earlier than usual, especially the audience from the East Coast of the United States, where it is in the early morning, I think. Thank you very much. Okay, today I would like to talk about the open-closed homotopy algebra in superstring field theory. This talk is based on this work. And so let me introduce a brief introduction and first, the content is a little bit technical. So I first summarized the contents of my talk and what I would like to say today. Let me start by a brief introduction. The question is why we consider the open-closed string field theory, which including both open string field and closed string field simultaneously, and then considering that they are between their interactions, the interaction between them. The reason is I think that the reason is explained from the two different viewpoints. From the open string theory perspectives and the closed string perspectives. First, from the open string theory perspectives, the reason is that to enable the manifest factorization of closed strings appeared in the quantum open string field theory. First, that we know that pure open string theory cannot be unitary. It is first proved by old work by Kaku and Kikawa. It is the pioneering work of the string field theory, the light-cone gauge string field theory. Furthermore, the Witten-Kubin string field theory contains only an open string field, but develops the closed string poles at one loop level. It is proven by Giddings, these guys, Giddings and Martinek and Witten. Yeah, considering this, for example, these types of Feynman diagram, 2-point Feynman diagrams with that non-planar Feynman diagram, that is written in this form. Open string comes in and makes the one loop, and the open string again going out. This circumference is that propagate loop time by propagating open string time. This can be in the limit of the t is equal to tends to 0. That is conformally equivalent to the long closed string propagation. So the diagram develops the closed string poles. So we need to incorporate closed string field to calculate S matrix at loop order by conventional LSD formula. Anyhow, we must introduce in some sense that the closed string field as an external field. Secondly, from the closed string perspectives, the reason is to incorporate the non-trivial different backgrounds. The open-closed interaction describes the interaction between closed strings and difference. That is first pointed out by Barton-Zwieback. And also some non-perturbative effects are also incorporated via the instanton calculation proposed by the work by Ashok. Okay, anyhow, these can be realized by quantum open-closed string field theory, but in this talk, we consider only the classical open-closed string field theory as the first step. Okay, so first summarize what I would like to say today. we introduce both open and closed string fields. Open string is denoted by psi. Closed string is denoted by phi, because that phi has this open, and the phi is denoted by this closed string. And the symplectic form is with this capital Omega. And introduce the interactions. There are two types of interactions. One is that the closed string interaction with n+1 closed string interaction. That is described by so-called vertex or map Ln that maps the n closed strings to one closed strings. Input is n closed string and output is one closed string. The other type, the new types of interaction is the n closed strings and L+1 open strings. The input is n closed strings and L open strings. The output is that one open strings. The open strings are attached to the boundary of the disk, and the closed string is attached to the inside of the disks, which we denote the NL. This is the string denote these string products. Describe these types of interactions. Then we can make the classical open string action by using this n type this vertex with this form. This action is invariant under this gauging transformation. But here the open string psi is a dynamical field, but the closed string phi is a background field. And this action represents an open string field theory on general closed string background. Closed string background satisfies this closed string equations of motion. Okay, if Ln and n and L satisfy the cyclic and open closed homotopy algebra, this is the cyclicity, this n string product is cyclic with respect to the open string side. And string products L and M satisfy these types of open closed homotopy algebra. The first one is that closed string so-called L infinity algebra, and the second one is the new one, including both L and M. This is that open closed homotopy algebra, or briefly OCHA. It is proposed by Kajiura and Stasi. Yeah, and for superstring field theory, open string field psi and closed string phi have several components with picture numbers and satisfy some constraints. The open string field psi have two components, NS sector, NS component psi NS representing the spacetime bosons, and among component psi R representing that spacetime fermions. And closed string has four components. The NS component are among NSR RR component. And NS and RR representing the spacetime bosons, and the RNS and NSR representing the spacetime fermions. And so we must distinguish these sectors in these string products L and N, and give these L and N their own picture numbers so that the output is consistent with the constraint and have correct picture numbers, like this. These subscript 2R or 2R bar, 2R represent that so-called Ramon number, which I will introduce shortly. Definition is introduced shortly. And number n minus r in the subscript, this brace at the subscript represent that the proper picture number of the string products. So the procedure I want to give you today, the assuming from the assumption, assuming the bosonic ocha that is given by this string product without picture number is known. That is easily constructed by if we know that bosonic string interactions. And then we will provide a prescription to give these types of string products by appropriately inserting that the picture changing operator X and C0 mode. That is I want to give you today. Okay, so let me start the content. Okay, starting from some basic matters, introducing some basic matters. As mentioned earlier, the open string has two components, Buchwald's and the Ramon component. That is in the open string Hilbert space with some restriction. And the cross string field has four components. That is in the cross string Hilbert space with some constraints. Introduced shortly. This string fields has ghost number 1 for open string, ghost number 2 for cross strings, and these restricted Hilbert space subspace of the open string and cross string Hilbert space restricted by this constraint, some projection, invariant under some projection, which is introduced shortly. And we also have specified the picture number in each component. In the open string, the Buchwald sector is represented by -1 picture Hilbert space. And Ramon sector is represented by -1/2 picture. And cross string, each sector has these picture numbers each. -1, -1, -1, 1/2, -1, and so on and so forth. And this constraint is represented by the picture. This projection operator Pxy is defined by these equations. Pxy is GO inverse, and Pxy cross is G cross inverse. And the GO and G cross is defined by each component as these equations. This means that and XO is the picture changing operator in the open string sector, and YO is the picture changing inverse of X in the open string sector. And GO is define this equation that is collectively represented by that both Buchwald and Ramon sector. This pi is that projection operator to the sectors. So pi 0 is the projection operator to the Buchwald sector, and pi 1 is projection operator to Ramon sector. So GO is acting on psi. GO is acting on one identity operator in the Buchwald sector, and XO picture changing operator X in the Ramon sector, and the inverse is also this one. And the cross string sector is that similarly we are also similarly introduced that the G operator G in the cross string sector. But string slightly different point is that inverse changing operator should be this non-local type. We have to use that this non-local type inverse picture changing operator because that these types of picture changing operator is not consistent in the Ramon sector. Okay. That if we define this GC on GG inverse, it becomes that picture. This operator G and G inverse satisfy that this projection property, and G is commute with the BRST charge. Then, yeah, we impose this constraint, in particular this constraint. If we impose this constraint, under this constraint, the string field, we can expand that each string field, open and close string field by in the Gauss number 0 mode.
Sorry to interrupt you, Hiroshi. Can you explain why you're doing this? Why do you do this projection?
Reason?
Why are you doing this projection? What is the reason? I've never seen it before. I don't know if it's common, but what's the motivation?
Motivation. That is first comes from the some kind of gauge invariance. That, for example, that Witten's first superstring field theory that has that inverse picture changing operator in such kinetic term, Ramon sector kinetic term has a Y insertion. And that has that some kind of gauge invariance due to the kernel of the operator Y. So that is equivalent to impose that these constraints.
So you claim this projection is preserved if you multiply string states?
No. This is this restrict that string field in this form.
I thought there was a problem. So, okay, I mean, this was a long time ago, but there was a problem with truncating out states, right? To try to, I mean, you have to show that the truncation is consistent, right? Is that something what you're trying to do now? You're trying to truncate out states, which will somehow allow you to inverse operators?
Yeah. There is several historical reasons. First of all, Professor Kazama and his collaborators found that we need only that these components psi r tilde, two components. If we expanding that string field in the Gauss zero modes, because that bosonic zero mode has due to the bosonic zero mode, if we expanding the string field in the Gauss zero mode, we have an infinite number of components. But Kazama et al. Found that only two components is enough to make the free Ramon string. That is one reason. And Witten's first open superstring field theory has also has only two components in the kinetic term. The string field have infinite number of components, but the kinetic term has almost all is does not in the kinetic term, but only two components in the kinetic terms. The almost all the components is in a sense, dummy, not appeared in the string field theory action. So we first we import the constraint from the first.
Thank you.
One
Yes.
point, I think what Nathan was asking is whether it's closed under string product. I think it's not closed under string product, but this is like L0 minus constraint, right? That if you take two string fields which are L0 minus projected, we still have to make a L0 minus projection after taking the product. This is probably similar to that, right? That if you take the product of these two, it will not be of this form, but we again project.
Yeah, yes. That is coming from the fermionic moduli in the Ramon sector.
Yeah.
And that is first pointed out by Yuji.
Yeah.
Okay. Can I go ahead?
Yeah.
Okay.
Thank
you. Okay. Then that under these constraints, this string field has only two components, from the infinite number of components to the two components. Yeah, after relaxing the Gauss number restriction, we restrict the Gauss number now for classical strings, but after relaxing the Gauss number restriction and consider the constraint, the first and the second components become the field and the anti-field, respectively. This first component is corresponding to the fields, and these blue components corresponding to the anti-field, respectively, via the VB quantization on the gauge-fixed basis. Gauge-fixed basis is that the basis, if we erase the anti-field, then that action becomes the gauge-fixed action. That is probably not so familiar. And this correspondence is also seen from the structure of the symplectic forms omega below, like this. Yeah, we can introduce symplectic forms omega. Symplectic forms in that unrestricted Hilbert space is defined in this form as in the bosonic string field theory, or first introduced by Munich group, by Ted, Ivo, by using that so-called BTZ inner product. Then for closed string, we have to insert that C0 minus 0 . But in the natural symplectic form in the restricted space is defined by this inserting that inverse, G inverse in the middle. That means that the inverse exchanging operator in the Ramon sector. If we define this kind of natural symplectic forms in the restricted space, the inner product of the symplectic form becomes just this skew symmetric type form. This is just a field, the relation between the field and anti-field in the VV formation. And in addition, we also use the natural symplectic forms in the large Hilbert space. That satisfies if both psi 1 and psi 2 is the small Hilbert space. There is this kind of relation. G0 mode is saturated that these are related by this G0 mode insertion. Okay, then interaction with Ocha structure is defined by these multilinear maps. The first one is the closed string interaction. That is also used or appeared in the closed string field theory. We denote it Ln. That is that is a map, multilinear map from the in symmetrized product tensor product space to the one Hilbert space. That means that this n string field to the one string field, this Ln phi blah 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 phi n. The input is n string, the output is one string Ln. And we identify the L1. L1 is just a map from it a kind of operator acting on this Hilbert space as a BRST charge. And this wedge denote that the symmetrized tensor product in this form. Yeah, the second type interaction is the open-close interaction between the open and closed string interaction. We denote it M. We denote it by M. N is that the number of the closed strings. The L denoted the number of open string inputs. That map from this N closed string to L open string to the one open string. The output is open string. That is a little bit asymmetric between that open and closed string, but that is because that closed string is in some sense quantum effect from the open string viewpoint. And if n equal as the n number of input open string input is equal to the this is including that map from the map n is equal to 0, then that this represent just L open string to one open string, that is that open string interaction that represent an open string interaction and satisfying that the infinity algebra as we see shortly. So we also identify N01 to the open string BRST charge. Okay, and it is useful to use that this interaction is represented by these multilinear maps, but it is useful to introduce that co-algebra representation. It is defined as follows by using these linear maps. Because at the linear map, the input is different from the each linear map, multilinear map. So it is useful to use the co-algebra representation. That is, we use that as, okay, we define it as follows. Now, these interactions are represented by degree odd co-derivation acting on this symmetrized tensor algebra. That is defined by this formal sum of the all the Hilbert space, the tensor algebras of the number of open and closed strings. Then from these multilinear maps, we can define that this co-derivation operator, called co-derivation, that maps from this tensor algebra to the tensor algebra. Yeah, detail is not so important. And then if this co-derivation L and co-derivation N satisfy that in this talk, that this square bracket denote the graded commutator. So the L plus N, L and N has degree odd, then that this square bracket denote the anti-bracket, anti-commutator. So that means that L plus N is nilpotent. or this has L and N has different output. L has the output of L is closed string and the output of N is open string. So this nilpotent equation becomes decomposed. We can decompose this equation to two equations. L is nilpotent and L and N satisfy this second equation. If these condition holds, we call this Hilbert space and the set of these three is called OCHA, open closed homotopy algebra. And these have substructures, of course, that L satisfy the L infinity algebra. This is represented by this equation. And N with a small number of input closed string is equal to 0 is just an open string interaction satisfy the infinity algebra. That is also the substructure. If it additionally satisfies this cyclicity condition with respect to the symplectic form capital omega, that is naturally in the restricted Hilbert space, we call this set, including the symplectic form, is called cyclic OCHA. Okay, that is general properties of the open closed homotopy algebra, and we have to use this in the superstring field theory. The OCHA in superstring field theory must have some additional properties. First one is we need a cyclic OCHA with additional three additional properties. First, as I mentioned earlier, first, we have to distinguish the type of fields by components, Newton-Schwarz and Ramond types of sectors, assigning any of A, B, or both, any of Ramond number or cyclic Ramond number, or maybe both. The Ramond number is defined by that the number of Ramond inputs minus number of Ramond outputs. And cyclic Ramond number is defined by number of Ramond field inputs plus number of Ramond output. These two Ramond numbers are advantage, each has advantage and also the disadvantage. The first one, a Ramond number is additive in the commutator. That is a nice property. And it is not invariant under the cyclic permutation, like it is important in the useful in the to consider the cyclic property. The cyclic Ramond number is compatible with this cyclistic conditions, but it is not additive in the commutator. Yeah, and the second, these string interactions L and M have some appropriate picture numbers. Because, for example, that so that picture number is consistent in the string product. Yeah, for example, consider the open string three open string interactions in the NS. Non-output is NS. The open string NS component has -1 picture. So these two give that picture number at -2, but the output must has picture number 1. So the these open string interaction, vertex must have subpicture number 1, and so on and so forth. This is given by this constraint for closed string, and this is explicitly solved in the open close interaction. Okay, and this product also be consistent with this projection operator constraint, projection constraint, because that the input is in the restricted Hilbert space, so the output is also in the restricted Hilbert space. Okay, so sorry. Okay, so the purpose, the aim of the talk is to explain that how these we construct that the string interaction with the products is with these 3 properties from the bosonic one. Yeah, construction. Yeah, we first assume that L and N without picture numbers defined by these 2 equations is already known. This can be constructed, this can be easily constructed if you know that the triangulation of the bosonic moduli space suitable for the string field theory. That is, we assume that is known in the bosonic string field theory. For the open closed string field theory, the Barton-Twieback was discussed that how we construct the triangulation of the bosonic moduli space. Then, okay, step 1. We introduce this B and C string product degree of co-derivation B and C. That is slightly different with L and M. That is specified by the cyclic Ramond number, not the Ramond number. And consider the 2 co-derivations like this, O1 and O2. That is corresponding to the L and N. But this B and C is specified by the cyclic Ramond number. That is because that we can consider the cyclicity. We construct the cyclic interactions. Then that these have B and C have does not have a correct picture number, correct output of the picture number. These have a picture number deficit, the following picture number deficit. Please. That means that Nubu-Schwarz closed string interaction with Nubu-Schwarz output has no picture number deficit, but in the Ramond sector that has a picture number deficit 1. That means that for the interaction which we want to construct must have a output picture number. Ramond output picture number must be equal to -1/2, but Ramond output of this B and C has a picture number -3/2. So one picture number less picture number. But we consider it and first construct that. Yeah. Now open close homotopy relation. Yeah. For this O1, O2, this corresponds to L, this corresponds to N. And this, if we consider this cyclic Ocha, the Ocha relation can be written by using that the B and C is like this. A little bit complicated, but anyhow, we can rewrite this in this form, in this five equations. Sorry, this is equal to 5 equations. And here the bracket with superscript, this, for example, this 1, or in general that I and j is equal to 1 or 2 or k. This difference is that the intermediate state is a closed string and or open strings. CC is that the intermediate state is open string. And we also introduced that this subscript x. These are defined by inserting the projection operator, this type of projection operator, and also in the operator x for the subscript in the middle state, intermediate state. Then the co-derivation, and this co-derivation Q and eta act as a QC and the QC plus QC bar on the closed string Hilbert space and QO eta O in the open string Hilbert space. The former one, this former 3, these 3 is that just the L infinity relation of this O1 or derivation O1, which already appeared when we construct the type 2 superstring field theory. And the new one is that O2, and this relation is that the new relations. Okay, step 2. If we find procedure is explained shortly, but if we find B and C, such as B and C, then we transform them as by using this operator that is called the co-homomorphism of the co-derivation or L infinity Ocha algebra, using that also B and C. Then we have co-derivation. The second one become that O2 become that just operator eta, just eta. Sorry. And okay, if you find B and C, we first we can first make two anti-commute L and N Ocha algebra. This described with this combination and this combination. The first one is transformed by these homomorphisms to the L plus N. The second one is transformed just eta. Then this L plus N is nilpotent and commute with eta. So this co-derivation is in the small Hilbert space and nilpotent. So and also that in this form we can see that this form, the form in this G operator is nilpotent and consistent with the constraint. That is a procedure. Okay, so the problem is to find how to find this B and C satisfying these equations. Okay, so how to construct B and C? Okay. Yeah, as I mentioned that this B is in already appeared in the construction of the type 2 superstring field theory. So we assume that that is already known how to construct B, and we use that so-called symmetric construction proposed previously, and we will extend it to constructing that also C. First, we consider the two kinds of generating functions, B S bar T and C S T, by introducing that parameter S bar and T. That T count at the picture number, total picture number, P plus P bar, and S count at the picture number deficit. And then that Ocha relation, this relation is also extended to this form by consistent with from the consistency of the picture number and picture number deficit and so on and so forth. With that, these projection were some operators in the middle. We define that commutator with these insertion. This relation interpolate the superstring Ocha relation at S bar T equals 0, 0, 1, and the bosonic strings Ocha relation at S bar T is equal to 1, 1, 0. So we can, by because due to this extension, these extension, we can construct the superstring Ocha B and C from the bosonic strings Ocha. And I cannot explain that how I found that relation, but the fact is that if B satisfies these differential equations of T S bar in this form with some insertion in addition to this some G operator insertion with by introducing some degree even co-derivation lambda and lambda bar this form, and this is the how we construct interaction B in the symmetric construction of the type 2 superstring interaction. And we also this time we also assume that this differential equation for vertex C by introducing that corresponding gauge product, this form. Then this left-hand side of these equations, a derivative of this left-hand side of these equations here are proportional to this themselves or their S interaction. Sorry, T derivatives. Their T derivatives is equal to themselves or their S derivative. So the explicit form is here. This implies that if these left-hand side of the relations is equal to t is equal to 0. Initially, it is equal to 0. Then any later time that this relation is equal, left-hand side is equal to 0. So this is that relation we want to obtain. But however, this equation in the initial equation at t equals 0 satisfied by bosonic Ocha interaction. As I said, that this t parameter counting that the picture number p and p, then p is equal to 0, then that t is equal to 0, then p is equal to 0. So this has a picture number 0. Both are picture number 0, so we can identify them to the bosonic interaction. And feature, these are known by assumption. Therefore, we can obtain that these generating functions by solving the differential equation with these initial conditions. That is known by assumption. Yeah, that's all for in the procedure, but just 1 hour. Yeah, to solve the equation, we can of course solve the equation recursively, and I will explain it a little bit more explicitly. To solve the equation explicitly, we first suppose that those for the L infinity algebra are already solved by B lambda solved. That means that the B lambda bar are given. Then rewrite the equation, differential equation for C as this is the second equation, second differential equation by expanding by the T. That complicated. And the first one is the T derivatives becomes this algebraic form and then this components. Yeah, from the first equation at p equals 0, this equation for p equal to 0, almost all the equation, including the sum, vanish, and only that the first term is remain. First term remain. Then that is that can be easily solved by this form. The C0 is equal to we set that C0 is equal to bosonic interaction, and then obtain by substituting this solution in the right-hand side of the second equation at p equals 0. This equation p equals 0, we obtain that C1. C1 is equal to has this form. The quantity in the right-hand side is all the quantities are known. Then we obtain that C1. And repeating the procedure, we next obtain the new 2 from the second equation at the p equal 1, and then obtain the C2. And so on and so forth. Or more explicitly, this CP can be expanded as a number of inputs. And first, first two component, first two has this component, has this form. C100 is equal to this form, and C101 is one component. The sum is sum of the Ramon number, some cyclic Ramon number, and so on. And the first component, those we want to know. The others are necessary for the intermediate steps. Okay, using this, okay, we construct the B and C, and we can construct the L and N by co-homomorphism or similarity transformation. Then we can define the action with the Ocha structure in this form, which is invariant under this gauge transformation. Here, where that phi BG is a background closed-string field satisfying the nonlinear equation of motion, this closed-string interaction equation of motion. And in addition, that the co-derivation with this form, including that the background field, as the co-derivation acting on this open string tensor product, tensor algebra, define the weak A infinity algebra, or weak A infinity algebra deformed by this background field. And we also must point out that this equation has a tadpole term coming from this open closed string interaction. So psi is equal to 0 is not the solution of psi equation of motion of this action. Psi equation of motion of this action. So we must shift psi for perturbative calculation. This kind of consideration is given by Carlo and his collaborator, and given in the talk this journal club before.
May I ask a question?
Yes.
Have you also consulted open closed superstring field theory?
Yeah.
I mean, you seem to you seem to treat the closed string as external field at this point, but then
Yes.
and up to the previous slide, I thought you were treating closed string as dynamical, and that doesn't seem to be any problem. So have you also consulted open closed string field theory with closed string dynamical closed string fields?
This is a open string field theory with background closed string field. So, and
why is that? Yeah.
Why?
But is it also possible? Is it also possible to consider open closed superstring field theory with dynamical closed string field?
Yes.
If
but,
you include L.
No. We have to include the quantum interaction. We have to extend that Ocha relation to the quantum Ocha, including that.
That's the reason you only consider open string.
Yes.
The dynamical open string. I
Yes.
see. But what is the situation in the bosonic open closed string field theory? Open closed bosonic string field theory.
The same.
Is it the same? Okay.
Yes.
Thank you.
Yeah. Okay. That's almost all I have to prepare for this talk. In the last, we have to outlook, give some outlook, and as from the question by Oka-san, that we have to further consider gauge fixing, loop quantum interaction that we have to fix the gauge and loop, and we also have to extend that L infinity or orchard algebra to the loop algebra, or that means that the BV equation to the quantum BV equation, and also that the closed string field theory have some problem with spurious pole problem that is discussed by Ashok and his collaborators, and also that the TED or some guys discuss with that problem. We have to carefully consider some spurious pole problem. That is not so clear, at least for me, that this algebraic type construction can be also used for some such kind of loop algebra, and that I want to consider some concrete analysis using this superstring field theory. We now have some several string field theory, then that we want to use that as some dynamical problem. In the perspective point of non-perturbative point of view, that we want to consider some classical solutions for cross strings and dualities, and more ambitiously that some ADS-CFT correspondence or some D instanton calculation and so on and so forth. And except for the non-perturbative analysis, but we also want to consider, we also have several problems for perturbative calculations. For example, that the off-shell amplitudes or some infrared divergences and so on, as already discussed by Ashok and his collaborators. So we have so many remaining issues to study. Okay, that's all for today, I want to say. Thank you very much. A bit earlier, a bit faster. I'm sorry. Do you have any questions?
Can I ask a question?
Yes.
So about these spurious poles. So it appears to me, so you're working in this restricted Hilbert space, I understand, no?
I'm sorry, say
so
again.
I presume that you work in this restricted Hilbert space in this construction, I think. No?
Yeah, yes.
And so I'm assuming that you then do these picture changing operators. You use perhaps the zero modes of the B ghost and so on. So is the spurious ghost, do they still arise in this when you actually work with the zero modes? Is that, I mean, maybe I don't know the answer. But.
I don't know. I also don't know the answer. It is, yeah, it is. I personally,
I think the spurious poles should still be there, right? I mean, why do you think it will not be there? Because zero modes, you still have to integrate. I mean, if you think of this as integrals along some contour, right? I think I would expect that you still have spurious poles.
I was just thinking because they're not
as all the
local
operators have zero picture number, I think the spurious poles are absent. But once you have operators carrying picture number, I think it's hard to avoid spurious poles.
So it's because the zero modes are not globally defined in moduli space, essentially. That's what you're saying.
Exactly, yeah.
And if you, So you have to somehow, at some point, you have to jump
Yeah.
when you. I was just thinking because they don't necessarily arise as local operators, perhaps, no? These picture changing operators. So then I thought perhaps the poles might not be manifest, but I would
Yeah, but my feeling is that as long as you have operators carrying picture number, even if they are not local, you probably still will have problems with spurious poles.
Mm-hmm.
May I make a comment on this?
Yes, go
Yeah.
ahead.
So in my construction of open superstring field theory with based on the supermodular space, I did with Cantor Omori, and the role of quadratic interaction correspond to just vertical integration in the perspective of this plays a role of vertical integration, just Ashok and Witten did. So in some sense, so there's there can be a spurious pole, but it can be avoided in a safer way. So that's that corresponds to the gauge invariance at the content of the open superstring field theory. And then it is, I think it is a very important open problem. So it can be avoided in this construction, but then it is very non-trivial question. That's I really wanted to explore in the future.
So you are saying you push the vertical contours in the interaction vertex. Is that the point? That
yeah. So from the gauge invariance, the quadratic interaction is required. And if you look at the role of the quadratic interaction in the perspective of the covering of the supermodular space, that really corresponds to the role of the vertical integration. Just you did. So even in if you use a zero mode of the picture changing operator, not the local picture changing operator, as you said, as Ashok said, there can be a spurious pole, but it can be double pole. Then we can avoid the spurious pole in a safer way. So that was the situation I worked with, and the situation the quadratic vertex I constructed with Cantor Omori, and I hope that it can be extended to the higher even quantum vertices.
So are there some vertices which you can construct explicitly in this theory and really write down a conformal field theory representation of it?
Yeah, that's what I did. Even only for the quadratic vertex for the open superstring field theory. And then so that but at that point it is very explicit. I think I proved that the possible spurious poles are avoided. Yeah. Just because the poles, there can be a pole in the construction of the, so the vertex is constructed as an integration over the some part of the modular space, and then actually we did find the pole, but we show that it is double pole. Yeah. So that's and it is I think it's very explicit because we use the it is an open superstring field theory based on the star product. So we know the conformal max explicitly, and we are working on the issue of picture changing operators. I mean, zero modes of picture changing operator. Then so I think, but then it is at this point it's very difficult to extend it to higher order unless we have a very nice without any strategy. I don't think it is realistic to extend it to higher orders. That's where I stopped.
And in Hiroshi's talk, that wasn't entirely obvious to me either. Can you explicitly construct these vertices or some of these vertices, or are there more formal objects that you discuss the algebraic properties thereof?
For classical algebra?
Yeah.
Yes.
So for instance, okay, I guess. So you can actually write down, say, the quartic vertex in your theory also.
Yes.
But probably stops at some point also.
Yeah, but in principle, we can calculate that. And I also have a question to someone that the expert of the superior spore problem, but maybe Ashok or Ivo, someone that do you think that this algebraic construction will fail at the quantum level? We now, with my graduate student, that we try to construct that interaction with satisfying that some loop algebra, and but I don't exactly know that there is any problem for coming from the superior spore. It formally we success that construct the interaction with loop, satisfying the loop homotopy algebra, but that is only formal answer, or?
I mean, with Ted Eller, at some point we tried to construct a tadpole in superstring field theory, and that's kind of, you know, we have a slightly different prescription where we integrate the picture changing operator over some contour rather than inserting it at some point. But we still run into obstructions because at some point they they start crossing into the vertex region or into the propagator region. So I think that's usually where the difficulties arise. They may not arise as singularities, but somehow it's not unambiguously defined at some point. I think that's so it's hard to define the vertices on independent of the actual calculation which you do. That's, I think that's the problem we faced at the time.
Yeah, but you may still be able to preserve the algebraic structure if we include the vertical segments in the definition of the vertices.
Yeah, I would think so.
Right?
Yeah.
I think that the spurious poles, I mean, are there, but I mean, they can be just part of the definition of the vertex. Right? So, I mean,
yeah, absolutely. I think the algebraic structure is there just to actually explicitly construct them independently of the moduli. The value of the moduli might be hard. I mean, that's in your thing, I guess. You solve that from the very beginning because you always make it part of the calculus. You only define the vertex once you compute, I understand, with the way you do picture changing.
Yeah.
You don't fix it before.
Yeah.
But now we only starting that the zero mode of the picture changing operator that has only finite degrees of freedom, no infinite number of degrees of freedom. So where does that thing infinity comes from?
Yeah, that was the origin of my first question. I was wondering why you would get a pole, but maybe it's more that somehow the integration moduli space don't meet, and then at some point you still have to do vertical integration, although you might not be manifested as a pole. Maybe that would be my speculation.
Yeah, because in the intermediate state, everything is propagating, right? I mean, your construction may involve just the zero modes, but you cannot prevent the other states to propagate in the intermediate state.
Yeah.
Yeah, it's like if you just think of joining a handle and you are supposed to sum over all states propagating in the handle, and that spectrum is unbounded from below, right? And there you don't, I mean, you can't necessarily impose the constraint that only the zero modes propagate. Yeah, as long as the handle is coming from a propagator, you can implement it. But sometimes the handle may be part of the vertex. Right? In the quantum theory, the vertex will also contain things like handles.
I see.
So I think Feynman diagrams with propagators, you can avoid spurious poles. But the vortices, the definition of the vortices themselves probably have to encounter, you encounter spurious poles. But I would think that the algebraic structure you can still preserve, even though you, I mean, you just include the spurious, the vertical segments in the definition of the vortex.
So you say that the algebraic structure is still work in the loop level or quantum level.
Yeah, that's what I would expect, that algebraic structure should still work at the quantum level, but the definition of the vortex will have to include these vertical segments.
I see. Thank you.
And in the end, it seems now that these constructions are clarifying many things, but whenever you actually do an explicit calculation, you have to break it down to some few fields which you actually consider, because doing the loops becomes too cumbersome for the whole string.
Yeah, I agree. Yeah, but I think that it is useful for some formal study, like unitarity of this matrix or something like that. Yeah, but the concrete calculation is quite cumbersome.
And then the objects n which you defined, they are basically the open closed vertices. Is that correct? These n coderivations.
Yeah.
And they map, is it the correct? So they map, if you want to have a classical open string field theory, you need to have that the classical, the open coderivations, they square to 0. I forget there were the m's for you, I think. No, the m squared to 0.
Yeah. Yes.
And that's mapped to a classical equation of motion in the closed string by these ends. Is that correct? That's basically how, I mean, it seems to me, no, that these open closed vertices somehow transport the classical closed string equations of motions into closure, or into closure of the coderivations of the open string. Isn't it? I mean, you probably find that the open string is only well defined if the closed string satisfies the closed string equation of motion, probably.
Yes, in the classical level, yes.
Okay, yeah. And is this a proof? Do you have a proof that this is really one-to-one?
I don't know exactly, but to show that this gauge invariance, we have to use that classical equation of motion, this equation of motion for the.
Okay.
Yeah.
I see.
We can only show that this gauge invariance by using this equation of motion.
I see.
Okay, I think Harold is having some microphone problems. Are there any other questions or comments? Well, if not, let's thank Hiroshi once again for his very nice talk.
Thank you very much.
I will stop the recording now.